Hello everyone. I hope you're doing well and hope you had a good Easter break last weekend. Okay, so this is the first video of week 14, and in this video I'd like to go over the slide for combined loading. Okay, so let me share the screen. Here we go. Okay. All right, so this is chapter 11, talking about the beam column. So we call this as a beam column because it works as a beam and also as a column at the same time. So in the previous chapter, we talked about the columns, and also we covered the analysis and design of the beams. And we only consider the columns with actual load only, right? We never talk about the combined loading between actual load and the moment. In the beam sections, we only consider the beam bending based on the moment only, right? But in reality, think about the frame. So let's say, here we go. So let's think about the frame, it's a simple frame like this, and whatever boundary conditions here. So these horizontal members we call the beams, and these vertical members are called columns. And in all your chapters, we talk about the columns based on the actual load, and these beams with whatever boundary conditions based on the transverse loading, which will provide a bending moment. We never talk about the actual load to the member, but in reality, think about especially this column. These columns are connected to the beams, and these joints are not always the pin, right? So in reality, we do have an actual member, the compression member, not only based on these actual forces, but also there are some moments transferred from the beams. So let me go on to the next page. So where does that combined loading come from? Column connections are not really pin, as I mentioned. So that transmits some moments, and which is the moment created by the transverse loading, and the loadings are applied on top of either slab or the beams, but that transverse load will create the shear force and bending moment, and some of those moments are going to be transferred into the column. And also the columns that are not loaded through their centroid. So for example, if we can imagine the column, let's say here we have some portion of the column. Earlier chapter, we talked about the actual force, which means the force is exactly applied at the centroidal axis. But sometimes we can have a situation that here we have a column. This is the centroidal axis, and the forces are applying on here. That means we do have a centricity that will create the moment, right? Moment, which is force times this moment arm, which is this eccentricity. So this will create a moment on this the column. Okay, so let's talk about the second order effects. Second order effects, I'm going to show you the diagrams later on, but elastic analysis requires the deformations to be small, which is the first order effect. In that case, we can ignore that deformation. So we never talk about that kind of deformation inside of our analysis. When a column begins to bend, an axial force not longer passes through the centroid of the column. I'm going to show you the example later on. That is called the second order effect. So second order effects are the changes in forces and moments as a result of the deformation. And rigorous analysis requires the solution of many differential equations using stability functions or wireframe analysis. And most commercial computer softwares are capable of doing this, but in the steel design, we will have a very easier method and very approximate method called direct analysis. So these are two examples of explaining about the second order effect. So the first one is based on the member effect. Okay, so let's see. So this is based on the member effect, which means think about this column. Top and the bottom boundary conditions are kind of restrained, right? So when we apply both actual load and the bending moment, due to these two combined loading, this column will be bent like this. So we do have a deformation along the length, especially in the middle, the center, that will that is the point where we have the maximum deformation. So due to this deformation, small delta, we will have additional moments here, which is P times delta, because this P is going to be applying through the centroidal axis of this column. So when I make a cut and draw a free body diagram, this is the original position of the column, but now this bended column look like this. You still have a P applied at here and the corresponding deformation in the middle, delta. So this P times delta will provide additional moment on top of whatever moments, which is the top end moment is M1, bottom end moment is M2. If we do have the same end moment, then it's going to be just the same level of the moments, and then we do have additional moment. In this case, we have M1 and M2, a little bit different amounts of the moment. In any case, we will have additional moment due to this deformation delta. And this is called P delta effect. And we use this lowercase Greek letter delta here, which is based on the member effect. The other case we call the structure effect. So think about this column. It's kind of a cantilevered, right? So there's no restraint on top of this boundary condition of this column. And then we apply both moment M and then actual force P, the same kind of a combined loading here. Because we do not have a restraint, the constraint at the top of the column, and there's the side sway is allowed, right? So the corresponding deformation is way larger than this small delta. That's why we use the capital letter, Greek letter delta here. So due to the structure effect, we use P delta effect. Due to the member effect, right, based on the fixed boundary condition, we do have a small, relatively smaller deformation. That's why we use a lowercase delta here. But both cases we call the P delta or the second order effect. So either P delta, that combine both P delta, the lowercase, and P delta, capital case. Okay, so we have to include these P delta, the second order effect, in our consideration. So this is the final equation that we're going to use in the analysis and design of the combined loading, okay, for beam column. So this is kind of a basic equation so let me correct this. This is not the exact equation. I'm going to talk about the exact equation that is provided by AISC, but this is the general form of the actual force and bending moment interaction diagram equation. So in this case, we have the ratio between these two P's with two different subscript here, R and C, and the same thing here, R and C for the moments, R and C for the moment, and these X, Y's are, of course, the bending moment about strong axis and weak axis. So basically these PR over PC, MR over MC for both X-axis and Y-axis, these ratios, sum of all those together should be less than or equal to 1.0, which will create an interaction diagram. And R stands for the required strength and C stands for the available strength. So basically the required strength means demand, and C represent available strength, which is capacity. So I'm going to talk more details when we get to the AISC equation. Okay, so this is the original format of the PM interaction diagram, and this is the simplified interaction surface. So here we have, since we have two different ratios for moments about x-axis and y-axis, that's why we have all three-dimensional the interaction diagrams are available. So here's the 1, 1, 1, right? So when you connect all these dots together, this will provide the domain of the capacity. I would say domain of the failure. So when the dots are inside of this domain, that means we are okay. Our capacity is not exceeding the demand. Otherwise, when you take the ratio between the capacity demands and is going to be the pointed outside of this domain, that means we are exceeding the limit. Okay, so this, I said that's the general interaction diagram, but in real case, that this is the kind of the relationship between the actual capacity to the bending moment capacity, but for both x and y axis here. Okay, of course we have this is W14 by 82 as a example, and you can see that here we have a typical shape of the y flange beam. This is going to be x-axis, and this is going to be y-axis, right? And x-axis is strong axis, y-axis is a weak axis. So, and we have a different sectional properties about these two axes. That's why we will have a different capacity, which is typical, right? And very obvious. So when we develop the normalized interaction diagram based on the ratio, so Pn, that's in this case, so yeah, this is the ratio between the capacity and demand. This is the ratio between capacity and demand for the moment, and we have an x and y axis curve. So AISC normalized the interaction diagram and simplified it into the two branches of the single linear straight lines. So this is the final result. So this is the important one, that now we have two different slopes, right? So we are going to start from 1.0 going down to 1.0 again, and x-axis is MR to MC, and we will have both MRX, MCX, or MRY to MCY. In any case, this MR and MC, so MR will be equal to either MU or MA, which means demand, right? So MU when you have a LRFD method, MA when you decide to use ASD. And MC, this is capacity. So for LRFD, it's going to be phi times MN. For ASD, it's going to be MN over omega. Same thing for this y-axis quantity. This is a ratio between PR to PC. Again, PR is going to be the demand. So this is going to be demand, PR. So for LRFD, it's going to be PU. ASD is going to be PA. So these two are demand. And here we have PC, which is phi times PN for LRFD, or PN over omega for ASD. So these two will be capacity, right? And we have to say that the capacity, we always compare the capacity demand. In this case, we're going to take the ratio between capacity and demands to create this interaction diagram. And this point 2 is the the guideline. So when you take the ratio between the actual load, the demand to capacity ratio based on the actual force, if that value is larger than or equal to 0.2 or less than 0.2, we have two different equations based on these two different slope, right? So when this ratio is larger than or equal to 0.2, then we have to use this equation. If this ratio is less than 0.2, then we have to follow this equation. Okay, and depending on which moments are applied, when you have a moment about x-axis only, then you're going to take this one. Otherwise, it's going to be 0. I mean, the moments about y-axis will be 0. When you have a moment about y-axis only, then these are going to be, we will have a ratio. This term is going to be 0 and vice versa. So when you take, so first of all, you have to take the ratio between the capacity and demand of your actual force. And depending on your value, you will follow these two equations. If you calculate this ratio and then take this, follow the equation, if the value is less than or equal to 1.0, that means your beam column is okay. Your capacity is larger than demand. Otherwise, you're out of this domain, which means your capacity is less than your demand. And the same thing here. So when your value is less than 0.2, then you have to follow this equation, right? So put all the numbers in this equation, satisfy this value less than 1.0, then your beam column is okay. Otherwise, you have to redesign or you have to increase the section properties or whatever, increase the strength. Okay, so that's the main thing. And then here's a couple of notes explain more details about the equations. I already explained about this. Available column strength PC, that is based on the axis with the largest slenderness ratio. Available bending stress MC, that's also capacity, is based on the bending stress without actual load. The required compressive strength PR is the second order force on the member. Required flexural strength MR is the second order bending moment of the member. Okay, so those are the capacities and demand. And in the AISC manual, they also provide an amplification factor, which will include the second order effect. Again, I already talked about the P delta effect. So since this MR in this equation here, MRX here, or MRY, right? Those should be the second order bending effect if there is any, right? And this is how we can find out the MR. So let's say here are the given moments, M1 at the top and the bottom of the column. And due to the actual force and this bending moment together, we expect to have a small P delta effect here. So MR can be the maximum moment due to the load, which is the bending moment, maximum moment here, which is going to be M1 plus this additional moment due to the second order effect P delta, right? So in the AISC manual, they introduced this amplification factor, which is called AF right here. And that is the ratio between MR to M1. And since MR is M1 plus P delta, right here, so we can simplify it as this AF amplification factor is going to be equal to 1 over 1 minus P delta divided by M1 plus P delta. Okay. And for the small delta, we can simplify it as AF of 1 over 1 minus P times delta over M1. So, and this is based on this P delta is going to be small enough so that we can approximate this delta over M1 plus P delta as delta over M1, then we can simplify it as this. So this is the amplification factor used in the AISC manual. Okay, and one more thing here, delta is equal to m1 L² over 8 EI. This is the typical equation given by the structural analysis, and we can even simplify it and approximate into this. Then our final amplification factor is going to be 1 over 1 minus P to PE, which is this PE from the Euler equation. So this is kind of the derivation, how we can calculate this amplification factor used in the AISC manual. I'm not going to go over the example problem using AF. I just want to introduce how we're going to include the second order effect. All right, so, and later the slides also talk about the formulations, how we can use it in the AISC calculations for the second order analysis. So you can just see it. What I'm going to do now is I'm going to go over the example problem in your textbook. So let's see. There we go. Okay, so let's look at the example 11.11-1 in page 362. So this is example 11-1. So the question is this: a 50 KSI W12/40 tension member with no holes is subjected to the axial loads PD and PL are given, as well as bending moments MDY and MLY. Is the member satisfactory if LB is less than LP? So there are a couple conditions here. So first of all, we do know the section, which is W12/40 with 50 KSI steel, okay? And there are two different type of load. One is axial load. The other one is bending moment. Okay, so this is combined loading, right? And axial loads are given as this: PD is equal to 25 kips. So this is dead load. PL is given as 30 kips. MD, and this is about y-axis, so it's MDY, which is 10 kip feet, and MLY, so this is live load, 25 kip feet. And one more condition, it says LB is less than LP. So you can imagine that you can think it as either column member or beam subjected to both bending moment and axial load. So in this case, let's say here we have a beam section under a certain transverse load that will create these two moments. And then in addition to that moment, we do have an actual force, okay? Oh, I said tension member, right? So it should be tension, not compression. Okay, and it says LB is less than LP. That means we can maximize our capacity, which is MP, right? Okay, so we can think it like this is our. I'm gonna solve for both methods, so I would say Mn will be equal to Mp, which is Fy times Z. Anyway, this Mn is going to be equal to Mp. So how can we solve this problem? Is the member satisfactory? That means I introduced those two equations, right? First of all, we have to compare the ratio between the actual capacity and demand to 0.2. So if the value is larger than or equal to 0.2 or less than 0.2, we have two different equations. So that's the first step. I'm going to solve this problem using which one? LRFD, ASD. I'm going to solve it with LRFD. So here we have LRFD. I'm going to use a different color for a solution. So red. Okay. LRFD. And the solution for ASD is available in your textbooks, and most of the procedures are going to be the same. So first step is we need to find out this. This is the first step. We have to find out the ratio between PR, which is the demand, and PC, that's the capacity. If this is larger than or equal to 0.2, then we're going to go on to the first equation. Less than 0.2, then we're going to follow the second equation. So what is PR? PR is the demand. So in this case, LRFD, PR should be equal to PU. That's the factor demand. And we have two actual load, 25 and 30. So I'm going to combine them using the load factors. So 1.2 times that load plus 1.6 times live load, 30. That will provide 78 kips. So this is our PR. Okay. And PC, this is, in this case, is going to be capacity. Here it is phi times Pn. And phi times Pn for the tension member. And there's no hole is set, so it's going to be the tension capacity against the yielding limit state, which is going to be Fy times Ag. So just look up the Ag, the gross area for W20 12 by 40, which is 11.7. So Ag is 11.7 inches square, and Fy is 50. So it's going to be 0.9 times 50 times 11.7. I got 526.5 in kips. So this is our capacity. So the first step, we take the ratio between PR to PC, and I have 78 for the demand, and the capacity is 526.5. The ratio between these two, I got 0.148, which is less than 0.2, right? So we have to follow the second equation, which looks like this. PR over 2 times PC plus, there's no coefficient in front of the parenthesis, MRX over MCX plus MRY, MCY. We have to calculate this, and if this calculation is less than or equal to 1.0, then our beam column is satisfactory. Okay, so we already have PR and PC, and let's calculate MR and MC. In this case, we do have the moment about y-axis only, so this is automatically going to 0, right? So let's calculate MRY and MCY. So MRY is simply MU, right, about y-axis. I'm going to call MUY, and that is 1.2 times that load, which is 10, plus 1.6 L, so 25. When you combine those two together with the factors, I got 52 kip feet. So this is going to be our demand. And MCY, which is capacity. So MCY, and in this case, LB is less than LP. LB, unsupported length, right? And LP for 12 by 40 section. Let me just look up the value. And you can find out LP. In this case, you don't need to look up this number, but I just want to give you an idea what it is and how we can find out those numbers. So this is under the beams. So 12 by 40 section. 12 by 50, 12 by 45, 12 by 40. So here we have 12 by 40 in table 3-2, LP value for 12 by 40 section, right? Yep, is 6.85. So I said you don't need to worry about this, but 6.85 feet, that is a given LP for this section W12 by 40. So we do not know what is going to be the unsupported length, but we do know, what we know is that LB is going to be less than LP, which means we can maximize our full plastic, our moment capacity, which is the full plastic moment capacity, which is this MP. So, but bottom line is MCY will be equal to phi times MN, in this case phi times MP, right? And about y-axis, so I'm going to put y here. So that's going to be our capacity, moment capacity. And when you go up to the table in chapter 3 in the AIC manual for W12 by 40 section for MP and the factor, the phi times MP, you can easily look it up as 63 kib feet. So this is going to be our capacity. So now just put these 4 numbers into this equation. So I'm going to use a different color now. So what is PR? PR is 78. PR here. And PC 526.5 going to here in the denominator 2 times this value. And MRY is going to be 52. And then 63. Just calculate all those numbers together. Then I got 0.899, which is less than 1.0. So therefore, our section W12 by 40, based on all these given conditions, satisfy that our beam column is good to go. So that's how we can solve the problem using this equation. Okay, there's one more example problem I'd like to go over, but I'd like to make a separate video clip for that. All right, thank you. See you soon.